Okay, so if there's no questions, I'm going to get into section 4.1. Chapter 4 is eventually going to be, you guys remember in pre-calculus when you learned about multiplicity, you learned about fundamental theorem of algebra maybe, when you had to graph polynomial functions. So you had to kind of know, find the roots, you had to factor it, maybe you learned synthetic division, right? All that kind of stuff? Yeah, so all that's going to come back. Yeah, and then on top of that, we're going to know how to graph based on calculus. How quickly is it rising? We're going to learn about the curvature of something. Right? Well, that's going to be exciting. We could, totally. Yeah, because it's real and it's not flat. It's crazy. Okay. So we're going to slowly build up that way. We'll start with something really, well, let's see what you guys think. Something we've sort of mentioned before. So we have this idea of max and min values. And there's actually a few different ways to, there's a few different types of maxes and mins. So let me draw a picture here. Let's see. That little weird dude. Let me change one little thing. Even better. Now, can anybody identify like what you consider to be a max? Yes.
The value with the highest y value.
Okay, cool. So you would say maybe this guy here is some kind of a max. So we'll call this x1. Some kind of a max. Does anyone else see something else? Yes.
Middle hump.
Middle hump? Oh, here?
Like a local maximum.
There we go. I like it. So this, if I live in a village here, wouldn't I think of that as being kind of, it's pretty tall compared to where I am. I would think of that as a local maximum, right? Like a local hill. Okay. And off in the distance I can see this insane thing, but I'm like, holy shit, this is good enough for me, right? So this is called an absolute max, which just makes sense. Is there any other y value over the whole domain of this function that gets higher than that one? No. So that is a local max. What kind of, can somebody think about what the definition of local max might be then? Absolute max is an easy definition. It's the biggest there. But what about local max? Go ahead.
Like the highest y value in a given interval on a larger function.
All right, like a sub-interval of the whole domain, right? So it's defined to be the highest output attained in a neighborhood. It's kind of crazy. So we call it like there's a little neighborhood around this. So it's like, let's call that point x2. So if f of x2 is greater than f of x for x near x2, then x2 is a location of a local max. So I put near. Near is one of those words that are ill-defined, like large. Would you consider 100 to be large? In some cases, yeah. But in some cases, 100 is stupid small, right? So near is sort of subjective to a certain degree. Okay. Maybe. You guys all? So on one level, this is pretty easy. You could pick them all out now, right? Well, where's a local min?
Those two that before the next two and the after.
Yeah, there's where the village is, right? That's a local min. And there's one there. Is there another local max?
above.
Yeah, up there, it's a local max. Where's an absolute max? I'm sorry, absolute min. It happens to also be a local min. Now let me ask you something a little bit weird. All right, is everybody cool with me so far? You cool with this? You know, like we don't know about you, but this is okay. Would you consider this to be a local max? Why is that one? You can't call it a local max.
Because it's not a neighborhood.
Yeah, if I try to create a neighborhood, this side of the neighborhood doesn't even frickin' exist, all right? Okay. Yeah, right? It's sort of like that one division. Oh, okay, so we got this guy. Okay, so it's pretty straightforward on one level. The hard part is, how do we, given a function, not a picture, but given a function, how do we find local maxes and mins? Yes? And let me give us another picture real quick. What's weird about this point there? Is there anything in terms of calculus that's weird about this point here?
It's a cusp.
It's a cusp, which means it's not
Differential.
differentiable. It's totally continuous. Totally continuous, right? They agree where they're going and they get there. It's not differentiable. Yeah, I like it. But is it still, would you call this a local max?
Yeah.
And an absolute max, especially if these keep going like this. So this would still be the location of a local max and an absolute max. Now, real quick, what is true about every single local max or min? What is true about them in terms of calculus? It's sure, the whole function is continuous. It's true. And they're differentiable, sure. What's true about the slope at those points?
0.
Yeah, the slope at every single one of these is 0. Yes?
Yes.
Okay. Can you, is everybody still with me? That kind of makes sense. The most basic maximum is like the top of a parabola looking dude, and that's going to be a slope 0. It's going to be a flat slope at the top. And the same thing for the bottom. There are weird situations where the slope is not 0. What is the slope at that point? Undefined. I love it because they don't agree. One thing is a really big positive, one thing is a really big, well, it's kind of weird. One thing is a really big negative, one thing is a really big positive, so they don't agree. They like it. So, let's develop a process. If I'm given a picture, that's easy. That's going to be the beginning of the homework, right? You say identify the locations of whatever. Easy shit. But if they give me a function, so let's take a step back in time. Does anyone remember from pre-calculus, if I gave you this function here, how to find the max or min? Can somebody tell me if this is going to have a maximum or a minimum? Can anyone tell me?
Minimum.
Why would it have a minimum?
Which is
Parabola.
Parabola that opens up, right? So in pre-calculus, we were finding maxes and mins, but we could only do it for parabolas. And obviously, is this a parabola? But does it have maxes and mins? Shit, yeah. Okay, so calculus, again, one thing calculus seems to do really well is expand on what we know already. So does anyone remember the shortcut to finding, and of course, what's the location of the min called for a parabola?
Vertex.
Min or max, yeah, vertex. Shortcut to find a vertex. Does anyone remember it was x equals, and it was a ratio.
Negative b divided by 2a.
Yeah, negative b over 2a. Does anyone else, does that sound familiar to anybody else? A little bit? I like, forget.
Looks a little bit like the
Quadratic.
like talking about.
All right, yeah. Real quick. Just because you brought it, no. Remember this beast here?
Ah, yes.
You see how there's negative b over 2a right there?
Oh.
You have a parabola. Stay with me now real quick. I'm going to bring calculus back into it in a minute, but you have a parabola. Sure. It's got x-intercepts. It could, right? The vertex would have to be right in the middle. Negative b over 2a, give or take this shit, yes? Isn't negative b over 2a plus this, negative b over 2a minus this, yes? So won't negative b over 2a be right in the freaking middle? That's how you prove this in pre-calculus, because we don't know calculus. How would we prove that in calculus? All right. Calculus, of course, makes everything much simpler. So what is this guy? This will be negative 12 over twice 3, which is 2, right? And then you would plug 2 back in to get the point, okay, to get the vertex, yes? Now, if I start with this, and what we just say for a nice thing like a parabola, what's going to be true at the maximum or the minimum? The slope is going to be 0. What's the slope of this?
3x plus b.
Set that equal to 0. What do you get?
B over 2.
Subtract b, right? Divide by 2a. What the shit? What the shit? Maybe? No? Yes? Maybe?
Yeah.
A little bit? Fine? It's not really David Blaine, but anyway, all right, so that's pretty cool. That's pretty simple, right? So calculus takes us beyond just being able to handle parabolas. Parabolas we can handle because we developed a way to find their vertex. But if it's not parabolic, if it's like this shit, I need some way. And so what it seems to make sense then is to take the derivative and set it equal to 0, or find where the derivative is undefined. Because that could be another location of a max or a min, right? Okay, let me stop for a minute. So what we've just done is we've talked about things we've talked about before, but we're putting them all together to create a process. If you give me a function and ask me what are the local maxes and mins, we have a process now to find those. Now real quick, if I set it equal to 0, is that necessarily the location of a max or a min? Does it have to be? Can anyone think of a really, really basic function that goes to 0, but it does not, it's not a maximum or a minimum? X cubed, yeah. So what does x cubed look like?
Like a elongated f. Like that.
Doesn't it go to 0 there?
And then it goes up.
And then it goes, nope, not going to turn. So that, the derivative is 0 at 0, correct? But is that the location of a max or a min? No. I like it. So we have a process. Let's think about this process. You give me a function. You ask me what are the local maxes and mins. I take the derivative, and I find a list of numbers that makes the derivative 0 or undefined. At that point, I still don't know the answer. But those numbers are the possible answers, are the possible locations of maxes or mins. We then still have to have a way to test them. Are they really maxes or mins, or do they just trick me? Okay. All right, I like it. So, what's true about the slope back here? Positive. And then, of course, right here it's 0. And then after that it's positive again. So the sign of the slope didn't change. If it's truly a max or a min, the slope, of course, is positive there. Negative there. Oh, shit. Okay. All right, so let's put this all together into a process, right? So I really want you to buy into the parts of this process. All right, so let me grab a function from here that I know will be semi-decent. Yeah, okay. What's this thing? X cubed minus 3x split from half. All right, so we have, so this is an example. X cubed minus 3x squared plus 1. Yeah, okay. And they give us an interval to work with. I'm not gonna worry about that yet. Less than or equal to it. So, let me ask you, I'm just gonna ask you to find the local max and min. Maxes and mins, I don't know. And by the way, let me just introduce this word right now. Instead of maxes and mins, I could just say extrema. Extreme X, extreme min. So extrema just captures the idea of extreme values. Higher way. So what's step one? Yeah, step one. Take a derivative, what do you get? I like it. Alright, and what's step two?
Solve for the zeros.
Or where it's,
Slope is 0.
Undefined.
so whether slope is 0 or undefined, and of course here, Carmen's looking at me like, this can't be undefined. Okay, cool, so we don't have to worry about that. But in general, you gotta worry, be careful. Make sure you get those points too. This guy is good everywhere. So step two is, find the zeros. Do that real quick for me.
Zero and 6.
6?
Or 2.
2? All right, what do you do to figure this out?
Oh, well, yeah, 0 and 6. Take out the 3x.
Take out 3x. Of course, you just factor this bad boy, right? So you get x is 2 or 0. Now this list, very small list, but that's okay. Very simple function. The list you get of all the x values that make the function's slope 0 or undefined, we call those critical numbers. Just because we want to pick something. So these are the critical numbers. Critical numbers are possible locations of maxes and mins.
So it's when the slope is 0.
Where the slope is 0 or undefined. In this case, it couldn't be undefined. But in general, where the slope is 0 undefined. I like it. Okay. So, can somebody tell me, based on what I said over here, this one did not turn out to be a max or a min because the slope was positive and then it was still positive. So is there a way to check this to see if they're really maxes or mins?
Plug them into the original function.
Not the original function. Because again, what was it here exactly? What were we looking at? The slope is positive, and then the slope is still positive. So I don't care about the original function right now. I need the derivative to tell me.
You do like a sign analysis.
Dude, what the shit? It's almost like I planted you out there. All right. I think we've done this once before in here, but in pre-calculus, you really should have done this quite a bit. This kind of thing. But now we're doing it with slopes. Whereas in pre-calc, you were doing it with values. So what's the slope at 0? 0. Okay. So put a little z there. What's the slope at 2? 0, because that's what we just did. Slope equals 0. And we got 2. So it's 0 there. Okay. So if it was undefined, what do you think I put up there? I put a freaking. Oh, okay. But just tell yourself what the shit's happening at those parts. Now, this is what we discussed before. This was related to the idea of multiplicity. I'm pretty sure we talked about multiplicity before. Do you remember? Does anyone remember multiplicity? What multiplicity means? No? Okay, so here's the idea. And we've talked about this before. The only way, since this function's continuous, the only way the slope could go from positive to negative is if it's 0 in the middle. Right? So that means that if I plug like a 1 in, where am I going to plug a 1 in, considering I'm curious about what the slope is? Where am I going to plug a 1 in?
Step 2.
Yeah, I like, or right here. So I'm going to plug a 1 in here. I don't care where the function is, I care where is it going, right? And this is why some of you guys have to really tighten your stuff up, because you're not telling yourself, what's the original function? Where did I take a derivative? You're going to really want to make that clear to yourself, because now you're going to have to plug it in one or the other, depending on what you're trying to find, right? So if I plug a 1 in, you plug a 1 in here, it's even better. This would be positive times negative. Is that cool? If I plug a 1 in, positive times negative. So it's negative everywhere in here. And then what if I plug a 3 in? Positive times positive. And what if I plug a negative 1 in? Negative times negative is crazy shit. Now, this is where I really wish you guys would embrace the idea of multiplicity. Multiplicity just means how often did a root show up? Aren't both of these to the first power? So 2 only showed up once, 0 only showed up once. Odd multiplicities change signs around their roots. If this would have been squared, this would have been the same sign on both sides. Even multiplicities, because what does this x squared do? Doesn't it turn? If it's positive, doesn't it stay positive after it's 0? Yes. What does a cube do? Odd multiplicities change signs. They go through. Maybe? So normally when I'm teaching pre-calculus, you talk about touching or going through a root. You either turn or you go through. Right? Okay. So, tell me this. We could even draw a really rough sketch of this thing. What does this tell me about the function? Can anyone tell me what these little plus signs tell me about the function? What's it doing?
As x equals negative, it's more positive.
What is this a plot of? I got the positives by plugging it into this, which was the slope, right? So this tells me the slope is positive, and then it's, what is it here? 0. And then it becomes negative, and then it becomes 0, and then it becomes positive, right? So what is this the location of? What kind of a extrema? It's a local max. You can just see that shit. It went up to it, came down from it. Maximum, right? So there's a max. Now, help me out. There's a max at 0 what?
0 to negative?
What's again?
0 to negative? No. 0 to negative.
No, careful. Not in the interval. This is a point. There's a max at
Oh, 0 to 2.
0, 1. Now I've got to plug it into this thing, right? Now I want to know, calm down, Jeff. Now I want to know where the function is, correct? Here I wanted to know what the shit is the function doing. So I had to plug it into this guy. Now I want to know where the shit is this function, and that's what this guy tells me, of course, right? So that's why it's so important. Some of you guys are really being evil to yourself, and you're just having derivatives kind of happen somewhere in the middle of shit. How can you keep track of what thing is which? And we're going to bring second derivatives in, so that you really want to tell yourself which one is which. Yes? So there's a max at 0, 1, and there's a min at 2.
-3.
Negative, oh. Just plug a 2 in here, right?
Yeah, I like it. Like it a lot.
All right, so you guys, before we come back and talk about absolute stuff, no. Stop it. Yes, okay, this is fine. Barfity barf. Yeah, okay, here we go. Here, you guys do everything we just did, but do it for this function here. Shit and a half. I need glasses, damn it. Okay, I see it. I think it's plus, is it plus? It's minus, damn it. There it is, okay.
That's 36, right?
36, yes. So you got your steps. So this is a nice polynomial. I'm going to sort of catch up to this. Beautiful polynomial. What'd you guys get for your critical numbers?
0, 3, and -2.
Now you gotta be careful. I see 3. I see -2. But the only way that 0 could be a critical number is if there was like an x here. Right? I only see 2, and I know, how do I know there's only 2 answers? I should only get 2 answers.
The derivative to the second degree.
Yeah, it's a second degree function I'm looking at right now. I like it. That's that fundamental theorem of algebra. Whatever the degree is matches the number of answers you should get for equal to 0. And they could be real, they could be complex, they could repeat. Tom, do you have a question? Okay. What do we call those things again? Did I already say?
Numbers.
Those are the critical numbers. So some of the problems in the homework are just going to want you to find the critical numbers. So that kicks ass. If that was the question, we would have been done. But that wasn't the question. Exactly. So finish that out.
Under the minimum, right?
Yes. All right. So here's the great thing about multiplicity. They're both an odd multiplicity. If I put a 0 in, I get negative times positive is negative. I know it changes sign. I know it changes sign. That's the beauty of multiplicity. Makes that much quicker. So then this is a, you can draw a little picture if you want to, but you should be able to tell me right now, is this, what is this, a local what?
That's a local max.
Up to it, down from it, local max. So, you know, it's not a bad idea to just go ahead and draw a little thing. It's flat there, it's negative, it's flat there, and it's positive. So then you know that's a max at -2 comma something.
44.
44? Sure. And then there's a min at 3, I should be more explicit here, local max, local min. 3 comma something.
-81.
Yeah.
Sure. Those certainly make sense. Could you have a problem where you have a local min that is negative, a local min that's positive, a local max that's negative? Totally, of course you could, of course. You could figure out how to draw that so you have like you can go down crazy. I mean, yeah, that could totally happen. So this seems like it makes sense. It's high, that's low. It's only 2, it's a simple function, so it kind of makes sense. But in general, don't go, oh, I must have made a mistake, because it could look funky. It could have little hills and valleys anywhere it wants to. Does that make sense? Okay, I like it. Now, let's come back. We haven't talked about what happens when you bring absolute max and min into it. Absolute max and min questions are beautiful. You're going to love them. When they have an absolute max and min question, they kick so much ass. Let's see if you believe it. Okay. Let's get a little bit funkier here. Yeah, why not? Let's do that one. That one looks really nice and funky. This one says find the absolute extrema. So whenever I say extrema, even if I misspell it, that means max and min. Right? So in the absolute extrema for this function on that interval. Now, let's see if you guys remember. Where could extrema occur? Where have we seen extrema occur? Like here, where could it occur? It could occur where the derivative is 0 or undefined. Or where else could an absolute extrema happen? Do you guys remember the one example I had earlier? I was like blah 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 and then I had this. Is that a local thing? No, it's an endpoint though. Yeah. Okay. Yes.
Could extrema occur on asymptotes? Is there any point?
Asymptotes, we officially don't consider, like if you had something like this.
Yeah.
This, I wouldn't call it an extreme value here because it never gets the value. It never gets to infinity, right? So there is no value there to call the extreme value. Does that make sense?
Yeah.
I don't know if you're talking about horizontal asymptotes.
No, that's vertical.
This one? Okay, okay. And there's another weird thing. What about, real quick, since we're talking about weird things, what about something like this? Is there an absolute, is there a local max or an absolute max to this? No. Because again, the possible winner doesn't exist. It's not defined. Does that make sense? So it's a lot like the one with the vertical asymptote. It just doesn't get there. So there is no value that's the highest. I like it. What about the one that's right next to this? I don't know if I want to go down this road. You guys are like, dude, it's been a week. I don't know. What about the one that's right next to that? There isn't one that's right next to that, right? Listen, I'm not going to go down that road. But if the only possible max has an open circle, there is no max. Okay. So coming back to this guy, here's the really beautiful thing. If the question says, find the absolute max and min, it is purely going to be plugging shit in, seeing what's the highest and what's the lowest. You just have to know what to plug in. So again, where could these occur? At the endpoints. So I'm going to plug 0 and 3 in. Or at the critical numbers. So how do we find the critical numbers? Derivative. I love it. Do it. Anybody here didn't get their test back last time? We don't want it. Makes sense. We don't all that. Makes sense. Now, of course, what are you guys using to do this derivative? Quotient rule. I love it. get this here. Because we get minus 2x squared plus x squared is negative x squared. Plus x minus x. So those cancel, then you get just plus 1 like this. Now we took the derivative. What do we have to do with it? Two things. Find where it's 0 or undefined, right? So how do I find where this is 0?
Factor the bottom.
No. That's where I find it's undefined. To find where it's 0, what's the only way a fraction could be 0? If the top is 0, right? So all I got to do to figure out where this is, so the critical number is going to come from either where f prime is 0, which will lead me to this, right? 1 minus x squared is 0. And please don't do this. That's shit. What did somebody leave out there? Plus or minus, I love it. Okay. Or where it's undefined. Could this be undefined? I mean, in general, yes, right? Because it's got a bottom. But can anybody, all right. So what's got to be true in order for this to be undefined? The bottom has to be 0. And the squared, I'm not going to worry about it. I'm not really worry about what makes that inside 0. Can anybody see really quickly that this is not going to have real answers? You guys remember what to look at to see if something has real answers, to see if it's even worth looking at? Remember the good old quadratic formula I had up here earlier? What part of that tells me if it's going to have complex answers? Negative b plus or minus square root of b squared minus 4ac over 2 anyway. So what's the only piece of that would make something not real? B squared minus 4ac. So if I do b squared minus 4ac, I get something less than 0. That would be complex. We're not doing complex calculus unless you want to. No, you don't want to? All right, fine. So we'll eliminate that as possibilities. So what are our only critical numbers then? What are the only critical numbers? 1 and negative 1. Are those both in the interval?
Oh, yes. Well, no.
Just 1.
Yeah, so I can eliminate negative 1 because of the interval they gave us, right? Yeah. Now here's the difference. If I wanted local max or min, I would have had to check that with the number line, all that kind of stuff, right? If they just say absolute max and min, I just need to see who wins. I know who's entered the contest. 1, 0, and 3 have entered the contest. I just got to plug them in and see who wins. Does that make sense? So when they ask you for an absolute max or min, you have less work to do. You just got to find the critical numbers and then plug those in along with the endpoints, because that's the only places that an absolute max or min could happen. So what happens? Let's see. So let's see who wins. 2 prizes here, right? Max and min. So what is f of 0? 0. What is f of 3? I don't know.
3 over 7.
3 over 7, is that right? Which I think is about 4.42 something. And what's f of 1?
1.
Yeah, 1 over 1 minus 1 plus 1 is 1. Okay. Is that right? 3 divided by 7? Anybody do that? Double check it. Is that like 0.42 something? Okay.
0.4286.
Look at that. I know how to divide by 7. All right, so who won? Who won the absolute min prize?
0.
Yeah, 0 won the absolute min. So there's an absolute min at 0, 1. 0. We already know. And so when the absolute max, there's an absolute max at 1, 1. So why did I plug a 0 in? And why did I plug a 3 in? They were endpoints. Why did I plug a 1 in? It was a critical number that was actually in that interval, right? Those are the only places that an absolute max or min can happen. I really want this to make sense. That's why I don't have to be as precise. Because there's just going to be one absolute min winner and one absolute max winner. And how do I tell who's got the biggest and lowest outputs? That's it. It's so much better, so much easier. Local maxes and mins, you got to make the number line, you got to be more detailed. Because now you want to know each one, what's happening at each one, not just who wins. Okay. Here, do this one. And then we'll do, yeah, but look at how much time. We got so much time. So everybody got this here. All right, so find the absolute maxes and mins for this little dude. On the interval 0.24. Is that right? Yeah. Make that better. So it's the absolute. Guys, let me ask you real quick. Everybody get this? Somebody tell me one critical number you can see right now without doing any work. 0, 11. We'll talk about in a minute if I'm going to keep it or not, but right now, 0 is definitely a critical number of this because it makes it undefined. Are there more critical numbers?
1 and negative.
Yes, how did you find those?
Plug in, 1 and
Oh,
negative.
no guess and check allowed here. But it's pretty simple, you can see there. But still, how would you solve this? What sucks about this equation? What sucks about it? Stupid x squared is on the bottom. Well, how do I take care of that? Multiply by x squared, right? So it's almost always, it's like, why do I hate this equation right now? Can I kill that? Yes, I can kill it. Yeah, it's awesome. Now again, it's not a life lesson. But in mathematics, you can get away with this. So if I multiply by x squared, and x squared minus 1 equals 0, and of course that's plus or minus 1 like we saw earlier. So the complete list of critical numbers are those. How many of those can we keep?
One.
Yes! And the answer to that question was not just the number of, but also the one. All right, so how do you finish this up? What's the next thing you do?
Plug in when and the endpoint.
Yeah.
To the original.
Here's the candidates. These are the candidates for winning the prize. These are the people that enter the contest. There's 0.2, there's 1, and there's 4. So you see what's f of 0.2, what's f of 1, what's f of 4, and then you see who wins. It's almost too nice to believe. 10/25. Is that negative 24? Does that make sense? 2/10 squared is 25. Negative 24, is that right?
Which?
0.2?
Wait, was that one over X? Oh, right, it was over X.
I'm sorry, I'm looking at the wrong thing. All right, now here's a really good place to do. So I gotta plug in here. That's better.
Yeah, that's kind of cool.
I got 5.2.
Yeah, so when you plug a 0.2 in, you get 0.2 plus 0.2 is 2/10, which is 1/5. So 1 over 1/5 is 5. So yeah, 5.2 away.
And then 4 is 4.25.
4, yeah, 4 plus 1/4, 4.25, 11. And then 1,
is 2.
yeah, 1 plus 1, that's amazing. So now you can just pick out the winners, right? So did this guy win a prize?
Mm-hmm.
Yep. He's an absolute max. This guy won absolute min, right?
And then before it gets the consolation prize.
And then this guy, no, he gets nothing.
Wow.
He ended the contest. Maybe. So that's kind of nice, right? Finding critical numbers, the only way they're going to be difficult is if you forget some algebra, you forget how to factor some stuff, forget how to solve some equations, right? Okay. So absolute max and min questions kind of kick ass. They're awesome. You're just going to plug in and see who wins. Local min and max, you have to be a little a bit more detailed because you have to analyze each of them. Yeah, okay. So let's do, I'm going to do a little bit out of section 4.2. And then we'll call it a day. 4.2 is titled The Mean Value Theorem. Say again?
It's a pretty mean value.
Yeah. So in this case, it's mean in terms of statistics.
Sorry, average.
Yeah. And it kind of, well, all right. By itself, it's okay. But it becomes the cornerstone of proving future theorems. All right, so I just want to kind of, well, anyway, let's see what you guys think about this. So it should be pretty straightforward. Now watch the conditions for this function, for this to work. Oh, this is funny. I wrote all these notes and I didn't refer to them. Did I do everything I wanted to? Sort of. Yes, okay. So, we're going to start with something. We're not going to start with this guy. We're going to kind of build up to this guy. So we're going to start with something called Rolle's theorem. And this guy, basically the mean value theorem and Rolle's theorem were kind of thought up at the same time. Rolle's theorem is sort of a specific instance of the mean value theorem, but it's a beautiful place to start because it's really straightforward. What it says is, if I have a function that is continuous on some interval AB and differentiable on, so they call this the closed interval and the open interval. So it doesn't have to be differentiable at the endpoints, but it does have to be continuous. Let me stop for a minute. So if I have a function continuous on this given interval and differentiable inside that interval, right there, we should understand what it's saying is we have a really nice function. We have a well-behaved function. It doesn't transport somewhere, right? It doesn't go to infinity or do some weird shit. Yes? So it's well-behaved, which is really weird when it, I know. Does that phrase sound weird to talk about mathematics that way? It's a well-behaved function. Like, I mean, this function is not well-behaved. This function is not well-behaved. All right, I mean, that function, get out of here. That's bullshit function, get out of here. This function is well-behaved. And f of A equals f of B. So wherever it starts, it does some stuff in the middle, but it ends at the same place it started at, right? The same height. So one way you could do this, would it just a straight line match this idea? It would totally match this idea. That's the most well-behaved thing in the world. So if I have a function that's continuous, differentiable, and f of A equals f of B, then there exists C in the interval AB where f prime of C is 0. Okay. So get that, copy down. So all of a sudden I threw a derivative at you, right? So let's draw a few example pictures of a function that matches this idea. So I've got A to B. F of A has to equal f of B. So it has to be here and it has to be here. So the simplest way to do that is to have a straight line, correct? Yes? What's the slope of that line?
0.
0. So is there a C somewhere in here where the slope is 0? Yeah, every damn one of them I could call C. So does there exist a C where the derivative of the function is 0? Of course, the whole damn thing. All right. Doesn't have to be a straight line though, does it? What else could it do? So I gotta be here. Gotta be here. What could it do? Couldn't it do this? What does it have to do if it does that? Could you just keep going up forever? No, because it's got to meet this condition here, right? So what does it eventually have to do?
Come back down.
Shit. Is there a position in there where f prime of C is 0? Is there a C somewhere in here where the derivative is 0?
Yes.
Yes. Right here, roughly, right? Could there be more than one? Of course, we just saw there's an infinite number of possible C's here, right? And couldn't you just connect this with a sine function or something? And then there would be a lot of answers for, you guys kind of get the idea? This should be remarkably, like, almost done. Do you understand? Because if you start to turn away from it, you have to turn back to it, and that turn back to it means you're going to have a max or a min. You're going to have a critical number. You're going to have that. Could I, according to what that says over there, could I have done this? Why not? What does that break?
Differentiable.
It's not differentiable. All right. Could I have done, this will be an easy one. I just want to show you. What about this? What if I do arrow. Is the slope 0 anywhere in the red line? No, it isn't. So I broke it. Of course, what the shit's wrong with that? It's not Continuous, that one's easy, it's not continuous. So if I force it to be continuous and differentiable, on one level, like I said, this is almost now, well, duh. Of course you're gonna have to find somewhere, you gotta come back to it. If you turn away from it, you gotta freaking come back to it. Somewhere there you're gonna have that turning point. At least one, you can do it multiple times. Now, let's make this a little more interesting. What if I take this out? Right? What if I take that out? And I'm going to change this. Okay, so that's Rolle's theorem. Right? Let me plot mean value theorem. So here's mean value theorem. And here's what mean value theorem really does. It does this. It looks at, well, damn it, Jeff. Let me draw a good one again. I took away all my good ones. Let me draw one that goes in. Okay, so there's a couple places here, right? And of course the whole idea is this. What's the slope between those 2 points? 0. So really, if I say this a little more generally, there has to be at least one place where the slope at this point is equal to the slope across the whole damn thing. That's a more general way to say it. It just happens to be 0. So what mean value theorem does is it does this. And it just looks at it sideways. So if you look at it sideways, is this slope 0 still? No. Right? If you take your coordinate system and you crank it, isn't that not going to be 0 anymore? So here's the idea. Let me draw the mean value theorem first, and then I'll put the theorem over there. So what mean value theorem says, I still have to have this bit. I want a well-behaved function so it can't transport and do all, right? Teleport. Can't do that. So I have to start with that. So if I have, these don't have to be equal anymore. Do you guys agree with me that there's a slope between these 2 points? Total, right? And again, even while I have it like this, maybe it's easier to think about this. If you do this, don't you make it 0? Don't you make it flat? If you kind of do your head like that, doesn't it become flat then, of course, right? Okay. So all mean value theorem does is it just rotates Rolle's theorem. So now, what's it say? This slope is no longer 0, is it? What is this slope? Yeah, what's this slope? Yes, cool. Y2 minus Y1 over? Yeah, that's the slope, right? Now, when this was true, the slope was 0, because that would be 0, yes? So what do you think this is going to say now? I've gotten established as the crow flies, but if my function doesn't follow that, if my function does something like this, there has to be somewhere where the slope at that point is parallel to this. When it was 0, I didn't have to say, I could just say, well, the slope is 0, 0, 0, 0. Now I've got to be a little more general in the way I speak. So it looks to be maybe about right there. Right? So there must be at least one place, at least one value, C, where the slope at that point is parallel to the as the crow flies. Yes?
Does that mean that there's also like a point that would be perpendicular to that line?
Oh, I see what you're saying. No. That's a more interesting question.
Like if you took C.
No, because I could just still have this be a straight line.
No, I know, but like say that is a straight line. The point of C to that straight line wouldn't have to be perpendicular.
Oh, I see what you mean. Yeah, this would have to be, if I drew this, okay, yeah. If I did the normal line at that point C, it would then be perpendicular to the as crow flies. That's just another, that would be the next step of saying it also does this. So it kind of makes sense. If I have any two parallel lines, then I drop 1 point down, it's gotta be perpendicular. Right, if I go the minimum distance between the two. Okay. Now, what did we just say? What did I just say? What did I just say about point C? What's supposed to be true about the function at point C?
Parallel to the slope.
The what of it at C?
Expand.
Sure, but so the slope of the function at C has to be parallel, which means equal to the slope. Hey, look at that. There's basically what the mean value theorem says. There exists this at least one C where f prime of C equals this guy as the crow flies. Crazy shit. And again, I really want you guys to see how this is just Rolle's theorem rotated a little bit. It's exactly the same theorem. Why is it a little more complicated? Because now it's not 0, now it's whatever the shit that is. But it's the same idea. Okay. Let's do one problem real quick. We haven't done an actual concrete problem yet. Bum, 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 bum. Bum, 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 bum. Here we go. No. There we go. Okay. All right, here we go. F of x equals square root of x on 0, 4. So it says, find the number C that satisfies the conclusion of the mean value theorem on the given interval. Why would mean value theorem work for this function? What's required? What are the two main requirements so this is a well-behaved function? It's got to be continuous. Is it continuous? Yes, remember that theorem we had a while back that's like polynomial and rational and radical and all that kind of shit. They're all continuous on the domain. So that's continuous definitely on 0, 4 because that's part of its domain. And it's got to be differentiable, and of course that's differentiable. Kick ass. So I want to apply this then. Can we just figure out the slope of the points from 0 to 4? I can just do exactly this, yes? F of 4 minus f of 0 over 4 minus 0. So what is that slope as the crow flies? And again, if you want to draw the picture, got a square root of x. I'm trying to figure out this slope. Right? So what's f of 4? 2. And f of 0, of course, is 0. So I get 1/2. Is that cool? I like it. And we've seen this kind of idea before in the homework, where I have multiple ways to look at the slope of something. One way to look at the slope of this problem is the dotted line. The other way is the tangent line that wants to be parallel to that. What do I have to do to this to start talking about tangent lines? Take the derivative. So I get
x to the power negative 1/2.
and what do I want that to equal? I need f prime of c. What do I need f prime of c to equal? 1/2. So I want 1/2 c to the negative 1/2 to equal 1/2. Oh my God. Frickin' 1/2 lover's dream. I love the number 1/2. This is fantastic. Automatically, this poor person is going to have to kill. Oh no! And this one you should be able to reason out pretty easily. What do you take the square root of and flip to get 1? 1. Yeah. You guys okay with that? Or you could do raise both sides to -2 power. Wouldn't that kill this? 1 to any power is 1. So, and sure enough, that's roughly where I drew it, isn't it? That's kind of neat. My shitty ass drawing, and it looks like it belongs there. Maybe? That was a little quick. I'll agree with that. But the idea is pretty straightforward. Okay, and of course the homework's going to kind of push you a little bit. You're going to go a little bit beyond this, but you know, it always does. Should be exciting. I think that's enough. So, welcome back again from spring break. Right back into it. Yeah. Let me know if you have any questions, otherwise you're free to go.